start to move along. We up first right off the bat, we have Chathika Gunaratne, who's going to present on evolutionary model discovery on a theoretical model of ideological polarization in social networks. And several people who asked in the tools section about doing IGSS in different platforms. Chathika is actually a great tools implementer, and so has done some good work in this, including IGSS in NetLogo, right? Using some code he wrote in, it's Python, right? That modifies the NetLogo code. Is that correct?
Yeah, it's in Python.
Yeah, but he's working on getting all those projects up and available for everyone. But I'll turn it over to Chathika to take it from here.
All right, thanks so much, Bill. Hopefully you can see my slides.
Yep, all looks good.
All right, great. Hi, everyone, Chathika here. I'm a postdoctoral research associate at the Learning Systems Group, CSMD at Oak Ridge National Lab. And I want to talk a little bit about the evolutionary model discovery tool and give you an example of implementing evolutionary model discovery using a theoretical model of ideological polarization on social networks. And I think this segues nicely with the previous discussion on polarization. So that's great. So evolutionary model discovery is a experimental AI framework for performing IGSS on ABMs. It's implemented in, it's got a Python implementation, and it helps you analyze your NetLogo models. And if you want a comprehensive breakdown of what the tool does, you can check out my dissertation work. The framework was built as a part of my PhD dissertation, supervised by Ivan Garbay, who's also co-organizing this workshop. The inspirations for this framework are many. Two notable inspirations are, of course, Agent Zero by Josh, where he describes how a single agent can embed a orthorational cognitive model, and how we can produce interesting complex phenomena using different social, emotional, and rational constructs. So the idea of evolutionary model discovery is to take such agents and then try and quantify what factors that go into such an agent are important towards the generation of a target phenomena. And this is sort of what was discussed in pattern-oriented modeling when it was first put out by Grimm and colleagues. So these are probably the two biggest inspirations for evolutionary model discovery. It works in two stages, where you provide an agent-based model with an agent rule that you identify has to be better defined and grounded in theory. So it takes that particular agent rule and then it evolves that with genetic programming. And then the genetic program, of course, tries to produce optimal solutions, but more importantly, it generates this vast set of data on factor presence to simulation performance. And what I do there is I take that data set and then run it through random forest. And using random forest importance analysis techniques, we're able to identify which factors best explain the simulation performance variance. So a little bit more about how it works under the hood. As I said, rule evolution happens with genetic programming. So it's not, it's out of the black box domain. It's not a black box parameter tuning optimization exercise. Rather, it's white box and looks at changing the underlying rules with which the agents make decisions. So therefore, it, of course, has many more degrees of freedom. And now we're dealing with a much larger search space. So genetic programs use two major operators, such as which are crossover and mutation. And with a single crossover or a single mutation, you can completely change the phenotypic structure that you're trying to represent. In the examples that I have here on the slide, you can see how interaction terms are added in with just one step or taken out. So you can make these big leaps across the fitness landscape. And since we're dealing with such a big search space, we have to have, of course, some limits, and we use syntax tree depth in practice to come up with more reasonably small solutions that we can then use for factor importance analysis. Once we have this data set, we use a random forest, train it on the factor presence to simulation fitness, so that the random forest is able to predict the simulation fitness given factor presence. And then random forests can be used to identify the more important factors using permutation accuracy importance, which permutes the factors input to the random forest model, and does an estimation of how important the existence of a particular factor is towards a better prediction of the simulation accuracy. So last year at NDC for IGSS 2020, we presented 3 instances where evolutionary model discovery was quite successful. And Ivan discussed these earlier today, so I'll just brush through them pretty quickly. The first was the artificial Anasazi model. Josh, Rob Axtell, and some other colleagues have worked on this project. There's a fairly highly cited project and well known in the computational social sciences literature as one of the more foundational agent-based modeling work. And this model looks at social agricultural behavior of the ancestral pueblo. Now, in this model, there is a rule that says when a household's associated farm plot is depleted, move to the next closest farm plot. So instead of assuming that this rule is correct, we used evolutionary model discovery to factor in other hypothesized causal factors and test them for factor importance in how the ancestral pueblo select next viable plot of land to farm on. And what we find is that things like quality of soil and social proximity to other households is of high importance, more than the original factor of distance. So this is a very intuitive result, and it helped improve the performance of the artificial Anasazi model. We did a similar experiment with residential segregation, where we took a model that Eris Hatna put together and looked at what factors caused mixed patterns of segregation and integration. And what we find there is that resistance to move, aversion to crowding, and racial preference are great at producing these mixed patterns of segregation and integration, which are more like what we see in the real world data. And that all 3 of these factors have to be present together. It's the interaction of these 3 factors at the individual scale that cause these sort of patterns to emerge. We also used evolutionary model discovery on a model of prioritization of information for response under information overload on social media. And here we had a large data set as part of the social sim program by DARPA. And we extracted around 10 to the power 7 relationships and used a compressed version of that in NetLogo to understand what factors drive people to prioritize certain received information under information overload condition. And what we find is that recency overcomes many of the other factors that we considered, like homophily or popularity of a particular conversation that the individual might be exposed to. So This is an example of the type of results you would see with evolutionary model discovery. So given a hypothesized set of factors, this is for the Anasazi experiment, we had a certain set of factors, and evolutionary model discovery is able to tell you the relative importance of each of these factors towards the emergence of the macro phenomena of interest. It's also able to tell you at what level of presence these factors are considered optimal for simulation accuracy. And using these insights, we can then construct models that outperform the previous assumed rule that the original model had been using. So as you can see in the artificial Anasazi model, quality of soil and social presence were of higher importance. So models that use those two factors outperform the original model that considered closeness of the next viable farm plot. And this is just to emphasize the importance of factor interactions. So this is what we see when we apply evolutionary model discovery on Aris's model of mixed patterns of residential segregation and integration. We see that none of these factors alone produce mixed patterns. In fact, having racial preference alone gives us the original Schelling segregation model. However, when we have all of these, when we have these these three factors together within the model, then we're able to evolve. We're able to see the emergence of mixed patterns of integration and segregation start to emerge. So evolutionary model discovery works with an annotation system on NetLogo so that it's a little easier to use. It involves you tagging your NetLogo code with the what I call the evolutionary model discovery entry point. So which line of code you want to evolve. So in this case, you can see how I've used @emd to annotate the NetLogo code and indicate that I want to evolve the next line. And the system uses strong typing. So you have to provide a certain return type. And then factors can be, causal factors can be implemented as NetLogo reporters. And you simply, again, have to annotate your reporter with the respective annotations, and you do the same with operators. And again, you have to specify what types your factors return and what types of parameters are expected by your operators or your factors. And then once you have your NetLogo model annotated, you can put together your, you can use the Python library to put together your evolutionary model discovery code and start to evolve your model. You need to provide it a objective function. You'll have to set some hyperparameters for the genetic program and some conditions for setting up your NetLogo simulations. And once your model is evolved, it'll produce a factor scores data set, and you can use the factor importance calculator to train the random forests and obtain your permutation and Gini importance values. So this has been developed with user friendliness in mind, but of course, it's quite a new tool. So if you find any bugs, please post issues, ping me at the GitHub link on the slide. And the documentation for this tool is at the link there. So what I want to do is go through this theoretical model of ideological polarization that I put together to demonstrate how evolutionary model discovery can be used. So ideological polarization, as was being discussed a few minutes earlier, following the really good keynote, is the emergence of two or more groups where these groups have opposing stances or viewpoints on a particular concept or idea. And what I'm interested in here is trying to find out what cognitive biases could lead to a highly polarized society. So if we have a social network, how can the stances of a unpolarized society or partially polarized society become hyperpolarized? And also to see whether a homogeneous network could become highly polarized. So what I do is I using NetLogo, I put together a scale-free undirected network of 200 agents. And in this model, each agent adopts a stance between -1 and 1. And initially, stance is sampled from a normal distribution. And the model at the moment accommodates for up to 2 species. So speciation was something that we hadn't tried before with evolutionary model discovery. So this is also something I wanted to test out myself and see how we can speciate. So this model accommodates for 2 species, 1 or 2 species. And polarization is measured as the root mean squared distance from the median stance. So it's how far away you are, how far away the population is from a central stance. And I consider several cognitive biases as factors in this experiment: confirmation bias, attentional bias, anchoring bias, egocentric bias, conformity bias, cognitive dissonance, and recency bias. There are operators in place for executing 1 or 2 species, and there are operators for adding factors to a list and taking a mean. So it's a fairly simple a couple of operators that are being used. And with evolutionary model discovery, the idea is that we can have direct representations of these factors, which are, of course, derived from the psychology literature, and so that we can express our results in a human interpretable form when comparing factor importances. So instead of, so I don't want to put genetic programming grammar here, but very simply, an example rule syntax would look something like this, where you have either 2 species or homogeneous execution. And if it's 2 species, you would get 2, let's say, means of several biases for the 2 different species. And then if it were 1 species, you would get a list of 1 list of cognitive biases being averaged across. So of course, I'm not a psychologist by background, so this was my best understanding of what these biases algorithmically express as. And this is one of the grand challenges, I think, that we discussed, how we can have a better representation of these factors. And as Josh previously mentioned, can these factors even be ordered into a suitable factor space, if you may. So with that caveat, confirmation bias was assumed to lead the agent to try to adopt the stance which was closest to their own stance. Attentional bias was where, with confirmation bias, an agent would try to form a link with a neighbor of its existing neighbors with closest stance and adopt that stance as and report that stance as the result of that factor. Attentional bias would do the same, but on its current neighbors. With anchoring bias, and that particular factor would anchor onto one of the agent's neighbors and continuously report that neighbor's stance as his own stance. Egocentric bias would report your own stance. With conformity bias, you would adopt the most popular stance in your neighborhood. With cognitive dissonance, you would sever the link with a neighbor of opposing stance with the highest distance from your own stance. With recency bias, you would you would create a link with one of your neighbors of your current neighbors, and you would sever the oldest link. So you would extend your network, and then you would sever a link with the highest age in your network. So given these factors in the genetic programming search, executed 16 genetic programming runs with a population size of 20 and over 20 generations. I used a 1-point crossover and point mutations of 0.8 and 0.1 respectively. And what I see is there is a reasonable convergence to a mean polarization score of between 0.3 and 0.6, keeping in mind that the max possible is 1. So it was manually working through the model and just playing around with the factors. It was really hard to produce a polarized society by just trying to replace the rule with different combinations of factors. And apparently, even the genetic program found it quite hard to go beyond the average fitness of 0.6 per rule. So this goes to show how hard this problem seems to be with the given factor space. Maybe there are some other factors or operators that I haven't considered, which would have given a better, a higher polarization score. But 0.6 seems quite high. So using the random forest, using 500 trees, I created a random forest on the factor presence to simulation fitness data. Evolutionary Model Discovery does all of this under the hood. What I see is that egocentric bias and attentional bias are by far have the highest permutation accuracy importance. Confirmation bias and cognitive dissonance have a moderate importance towards production of a highly polarized society, while conformity bias, anchoring bias, and recency don't seem to have as much importance and have little to no effect. What I see with speciation is that having two species definitely helps. When the model is speciated, you're more likely overall to have a higher polarization score than if you're considering a homogeneous network. Analyzing the top 1% of the evolved rules, which accounts for 64 simulations, I see that, again, all of the top 1% have species being executed, and all of them have confirmation bias as one species. The other species changes from egocentric bias. It could be attentional bias. It could be the mean of, it could be executing the mean of attentional bias and egocentric bias. Or, I'm sorry, this should be cognitive dissonance. Or it could be, the second species could be executing cognitive dissonance, not attentional bias. What I see is that confirmation bias with egocentric bias is the more popular rule in the top 1%, followed by confirmation bias with attentional bias. So this is just a, sorry, I seem to have put attentional bias over here. But this is just
Chathika?
Yeah.
Just a quick comment, like if you could wrap up in the next 5 minutes or so, that would be great, so we can have some time for questions.
Sure. Yeah, almost there. Thanks, Will.
No worries. Just want to let you know.
Sure. So what I see is with the first three rules, egocentric bias with confirmation bias, or attentional bias with confirmation bias, or the mean of the two with confirmation bias, we get the confirmation bias-driven agents taking highly polarized stances, which has been sort of been pushed to the two ends by the second species. I'm sorry, again, this should be cognitive dissonance. what we see in the cognitive dissonance case is that the network actually cleaves in two, and we get two subnetworks. So when confirmation bias is combined with cognitive dissonance, the network splits into two parts. Yeah, so when I compare 100 runs of these four models, however, I find that there's no statistically significant difference between performance of three of these models, except the cognitive dissonance one, which is slightly overall slightly has slightly an overall lower polarization intensity. So the insights and implications here are that heterogeneity in cognitive biases are more likely to produce polarized social networks, and that individuals, when a social network has individuals with confirmation bias, and they're paired with individuals driven by attentional bias or egocentric individuals, then we're likely to see a certain set of individuals adopting extreme stances. If we have confirmation bias paired with cognitive dissonance, we see the social network cleave into two parts. And when we compare these first set of factors with conformity bias, anchoring bias, and recency bias, we see little to no effect of those three factors. So just to wrap up, future directions we're thinking about at Oak Ridge National Laboratory is we're talking about deploying this approach on computing resources that we have, like Summit, the supercomputer that we have in-house, which would definitely help with the theoretically infinite large landscape that we're dealing with. And we're looking at a model of bacterial growth with some of my colleagues, and thinking of themes beyond human social systems. And we're also looking at integrating deep neural network architectures in place of the genetic programming approach that we currently have. So with that, I'd like to take any questions, and thank you so much for your attention.
Sure, yeah, there's a couple of questions in the chat that came through. One from Eric. Eric, do you want to go ahead and just ask your question? Eric Scott?
Sure. So,
okay.
So yeah, I was searching for the mute button. I was, if I understand correctly, the random forests are being used strictly as an explanation mechanism here, right? To elucidate and analyze the results.
Yes, you're right. Yeah, it's for post analysis of the GP data.
Right.
Yeah, that's right.
Got it.
Yeah.
Well, the reason I'm focusing on that is when I first heard that you're using random forests to predict performance, my first thought was surrogate modeling. So using a predictive model to predict the performance so that you don't have to run so much NetLogo so many times. So I just raised that as an idea. If you want to push some of these past, 20 generations up into the hundreds or thousands of generations, a surrogate modeling mechanism might really be necessary for these expensive simulations.
Yeah, you're right. You're totally right. That's something that we discussed back at UCF, but we never got around to thinking of a way to generalize a surrogate approach. But you're right. That's definitely something that's worth looking into.
Or Mark points out, you could just use Summit.
Yeah, or you could just use Summit.
All right.
Sorry, I couldn't resist.
And then it also appears we have one question from Robin. Do you want to ask that question, Robin?
Yeah, I can do quickly. Yeah, so I think Chathika, great tool, by the way, as ever. I think my question was, at the start, kind of you're puzzling over how you might represent the different psychological biases, yeah. And I wondered if you'd thought about how you might, use IGSS to look at alternatives. So then they put a link in the chat to a study in Jazz where they looked at different theory of planned behavior implementations that produced, wildly different outcomes. So, and which one can you claim actually represents the mechanism? So have you thought about these kinds of alternative representations at all?
I actually haven't. I think I haven't come across that paper. Thanks for that. But you're right. The results are definitely sensitive to how you implement the factors at end, and that depends in turn on how well the factors are described in the literature that you're using. So yeah, there's definitely room for error or even just differences in how these things, these factors can be implemented. And it's almost as if we would benefit from having a library of such implementations that maybe drive us towards consensus, some consensus, and have a better, more robust algorithmic definition that everyone agrees on. But yeah, that's a really good point, I think, Carl.
Thanks.
Great. Okay. In the interest of time, I think we should probably move on to our last talk of the evening.